Let's discuss the concept of phase change in wave reflection. As we have just studied that we have the transmission coefficient for a wave incident on a boundary can be given as 2v2 by v1 plus v2, and reflection coefficient is v2 minus v1 by v1 plus v2, where v1 v2 are the speed of waves in the two media. In medium 1 it is v1, in medium 2 it is v2, and a wave incident, it is reflected with the displacement yr and transmitted with displacement yt. Here you can see whatever may be the values of v1 and v2, you can see that this at will be always positive, because here whatever be the values of v1 and v2, it will always be positive. That means we can say the transmitted wave will always be in same phase with the incident wave. Like if we are writing incident wave as a sine of omega t minus k1x, transmitted wave can always be written as at sine of omega t minus k2x. As there is a component of this wave, so we can treat the two as coherent waves, and here we can see that as at is positive, the two waves will always be in same phase. But if we talk about reflection coefficient, we can say if V2 is less than V1, this implies medium 2 is denser than medium 1. If in second medium wave speed is less, we can see if this part is less, AR will be negative. If AR is negative, this implies will be having a reflection coefficient will be equals to negative of mod of ARA. I've taken mod because the whole parameter will be negative, because the reflection coefficient is negative. This implies if we write the equation for reflected wave, it can be written as negative of ARA sine of omega t plus k1x. And this negative sign we can take in. This can be ARA can be written as AR magnitude sine of omega t plus k1x plus pi, because this negative sign is basically accounting a phase change of pi radians. Now if you compare this reflected wave equation with the incident wave equation, we can see that reflected wave is having a phase difference of pi radians with the incident wave. That means it will be in opposite phase with the incident wave. So here we can state whenever a wave is reflected from the boundary of a denser medium, the reflected wave will be opposite phase with respect to the incident wave. But if medium 2 is rarer or V2 is higher, AR will be positive, no phase change will occur. So here we can list it up in a statement also. Let's write down the next slide. So we can summarize the effect which we have just seen, that whenever we just keep it in form of a note, whenever a wave is reflected from the boundary of a denser medium, it suffers for a phase change of pi radian and is reflected in opposite phase with respect to incident wave. So you should always remember, if in medium 1 wave speed is V1, in medium 2 wave speed is V2, and say if V2 is more than V1, that means medium 2 is rarer, Then there's the incident wave, there's the reflected wave, and there's the transmitted wave. If V2 is more than V1 in this situation, we can see as transmission coefficient is always positive. Here reflection coefficient will also be positive because it is given as V2 minus V1 upon V1 plus V2. So if both are positive, we can say transmitted wave is in same phase over the incident wave, as well as we can write reflected wave is also in same phase over the incident wave. But if the situation is different, like if this medium 1, this medium 2, and here wave speed is V2, here wave speed is V1, and we are given with the V2 less than V1. This is the situation when medium 2 is denser. So obviously here transmission coefficient is positive, which is always there, but here reflection coefficient will be negative. So when a wave is incident, this incident wave, then the reflected wave will be in opposite phase with the incident wave, and transmitted wave will always be in same phase. So here we can write TW and IW in same phase, but here reflected wave and incident wave in opposite phase because here the reflection coefficient is negative.